Hello friends, welcome to Engineering Funda family. In this video, I will solve one comprehensive example based on linear block code. In this example, I will explain encoding and decoding process of linear block code. Means in this example, I will explain how to generate code word as well as I will explain how to resolve error as if we receive data along with the error. So in this example, I will explain each and every concepts of linear block code, and based on this example, you can solve any question based on linear block code. So I request you to see this video till last. Based on this example, you can solve any problems based on linear block code. So let me explain the question first. See here in question, we have 6,3 block code. What it means? It means here we have n, that is 6. N is total bits in given code and k is information bits, that is 3. Here we have been given with generator matrix G. First of all, you need to understand what is generator matrix. See, generator matrix, that is a combination of identity matrix and parity matrix. So if you observe, see, we have 3 rows and 6 columns. If you observe this portion, then this portion belongs to identity matrix. In identity matrix, we have ones diagonally and other bits are zeros. And over here we have parity matrix. So first of all, one should know what is generator matrix. See, generator matrix, that is a combination of identity matrix and parity matrix. So let me note down over here. See, we have identity matrix I of k, and here in identity matrix we have ones as per diagonal. So you can observe here we have 3 rows. So diagonally we have 3 ones and other bits are zeros, right? So this is identity matrix based on generator matrix, and here in this generator matrix we have parity matrix. This parity matrix, that is given by 1 0 1, then 0 1 1, then 1 1 0. That is given in question, right? See, based on this generator matrix, we need to understand all corresponding code vectors. So here I'll explain you how to generate code word. Let me explain that. See, if you want to generate code word, then code word matrix is C. And code word is information into generator matrix. So one should know by multiplying information with generator matrix, one can generate code word. And this multiplication, that will be information and PC. Here PC is parity of code word. So we will be having information, and based on that we need to understand how to calculate PC. Let me explain this calculation of PC. PC can be calculated by information into parity matrix. You can observe here we have parity matrix, and by multiplying information with parity, one can generate parity code word matrix. And if you have parity code word matrix, then one can generate code word. Sometimes you may be given with information. You can observe here we have 3-bit information. So if you have 3-bit information, then by directly multiplying 3-bit information with this G, you can generate code word. But here we need to generate all the corresponding code vectors. So here I'll explain you simplest way of calculation. See, here we have information I and parity P. And if you observe, see this PC, let us say this PC is P0, P1 and P2. Let us say here information I, that is I0, I1 and I2. And here we have parity matrix, that is 1 0 1, 0 1 1 and 1 1 0. Now based on this, one can understand P0, P1 and P2 calculation. See, if you want to calculate P0, then you will have to multiply this row with this column. So if you multiply this row with this column, then you will be having I0 into 1 plus I1 into 0 plus I2 into 1. Means we will be having I0 plus I2. And remember, this is modular to addition over here. So that will be XOR operation, right? Similarly, if you want to calculate P1, then that will be this row into second column. So here we will be having I0 into 0 plus I1 into 1 plus I2 into 1. So we'll be having P1, that will be I1 XOR I2, right? And if you want to calculate P2, then that will be this row into third column. So that will be I0 into 1 plus I1 into 1 plus I2 into 0. So this will be I0 XOR I1, right? So that is how one can identify parity codeword matrix, that is P0, P1, P2. Now, based on this understanding, we can generate codeword C. Let me explain that. See, here I'll be explaining you codeword calculation, and here we will be having information that will be I0, I1 and I2, and you can observe with codeword we have I and PC, and PC is having P0, P1, P2. So let me note down P0, P1 and P2. See, here we have 3-bit information. So data could be 000, 001, 010, 011, 100, 101, 110 and 111. And based on this data, let me note down codeword. Here we have C1, here we have C2, C3, C4, C5, C6, C7 and C8. So that is how in total 8 codewords are there. Now let us identify P0 first. See, P0 is I0 XOR I2. So I0 XOR I2. So that will be 0 XOR 00, 0 XOR 11, 000, 011, 101, 110, 101 and 110. If you talk about P1, then P1 is I1 XOR I2. So I1 XOR I2, that is P1. So 000, 011, 101, 110, 000, 011, 101, 110. And if you observe P2, then P2 is I0 XOR I1. So P2, that is I0 XOR I1. So that will be 000, 000, 011, 011, 101, 101, 110, 110. So that is how we can identify all the code words. So here in first question, we were been identifying all corresponding code vectors, right? Now based on code vectors, one can understand minimum Hamming distance. That even I have explained in my earlier theory videos. One should know Hamming distance, and Hamming distance is minimum weight of code word. So here if you observe, we have all the possible code words. So we need to understand minimum weight of each and every code. So here I'll calculate weight of each and every code. One should know weight is number of ones. See here, this first code word that is having all zeros, that we don't need to consider. So I'm marking dash over here. Then with this second code word, we have 3 ones. So weight is 3. Here we have 3 ones. Here we have 4 ones. Here we have 3 ones. Here we have 4 ones. Here we have 4 ones. And here we have 3 ones. So minimum Hamming distance, that will be minimum weight. Here with each and every code word, if you observe, minimum weight is 3. So here Hamming distance that is 3 bits, right? Now, based on having distance, we need to understand error detection and error correction capability. Let me explain that. If you want to understand error detection, then error detection that will be lower than or equal to d minimum minus 1. Here d minimum is 3. So one can say error detection that will be 3 minus 1, that will be 2. So here with this code, one can have 2 bits error detection. And if you talk about next parameter, that is error correction, then error correction is defined as lower than or equal to d minimum minus 1 divided by 2. Here d minimum that is 3. So 3 minus 1, 2 divided by 2. So that will be lower than or equal to 1. So one can say here with the use of this code word, one can have 1 bit error correction, right? Now let me explain next parameter. See, next parameter, that is to identify parity check matrix. Let me explain first what is parity check matrix. See, parity check matrix that is denoted by H. And if you want to calculate parity check matrix, then that is P transpose and identity matrix n minus A. So based on P transpose and identity matrix, one can understand parity check matrix. Here if you observe, we have parity matrix that one can have based on generator matrix. This generator matrix that will be given to you. So if you have this parity check matrix, then based on parity check matrix, one can identify P transpose, right? So here I'll be taking parity matrix, and based on parity matrix, let us identify P transpose. See, in P transpose, what we need to do? We need to convert rows into column. So here we have a row that is 101. Now that should be column. Here we have second row that is 011. Now that should be column. And we have third row that is 110. That should be third column. So now we have P transpose, and based on P transpose and I of n minus k, one can have H matrix. See here, if you observe the question, then in question we have 6,3 code, right? So based on 6,3, one can understand this calculation. See, this will be P transpose and identity of 6 minus 3 means I3. So this will be identity matrix, right? So I3 means here we will be having 3 ones diagonally. Let me show it to you. So now if you want to calculate parity check matrix H, then here we have P transpose, that is this. Let me note it down. 101, 011, 110. And then we have identity with 3 rows. So here with this identity, we have 111 diagonally and other bits are zeros, right? So that is how one can calculate parity check matrix. Now we have parity check matrix. So one can resolve error using parity check matrix. So if you observe next question, then in next question, we need to find error as if received code is 1000011. So if you want to understand how error is there, then we need to identify syndrome matrix. Let me explain that. So here, now I'll explain you syndrome matrix. This syndrome matrix that we use it to identify error. One should know, see this syndrome matrix S, that is a multiplication of received matrix into H transpose. So received matrix into H transpose, that will be syndrome matrix. Here if you observe received data Y. So what is that? Received data, that is 1000011. So let me note it down. See here received data Y, that is 1000011, and that we need to multiply with H transpose. So H transpose, that one can have based on parity check matrix S. Here we need to convert this row into column. So here we have first row. Now that I'll write down as a column. So we have 1 0 1 1 0 0. Now that I'll be representing by column. And this second row, now that will be second column, 0 1 1 0 1 0. And now this third row, that will be third column. So double 1 triple 0 and 1, that is our third column with H transpose. Right. Now simply we need to identify this multiplication. See this row that we will multiply with this column. Right. And then we will be having first bit. So here, if you multiply this first row with this first column, then 1 into 1, that is 1. Then 0 into 0, that is 0. 0 into 1, that is 0. 0 into 1, that is 0. 1 into 0, that is 0. And 1 into 0, that is 0. So here we have 1 time 1. Means this bit is 1. Now for second bit, we need to multiply this row with second column. So here, see this 1 into 0, that is 0. 0 into 1, 0 into 1 and 0 into 0. And then we have 1 into 1, that is 1, and 1 into 0, so that is 0. So one time again we have 1. So here we need to write 1. And for third bit, if you observe this row and this column multiplication that we need to perform. So 1 into 1, that is 1, 1 time 1. Then 0 into 1, 0 into 0, 0 into 0, then 1 into 0 and 1 into 1. So 2 times 1s are there, means it will be 0. The reason is here we perform modulo 2 addition, or one can say XOR operation. So 2 times 1 means it will be 0. So now we have error matrix, right? Or one can say syndrome matrix. And based on syndrome matrix, we can identify location of error. And that one need to understand based on this H transpose. If you observe, see, we have this calculation, right? And if you match this 110 in this H transpose, then that is available over here, right? It is available at third location. Let me note it down. What it means? It means we have error in third bit. So this is what we have received. And here error syndrome, that explains here we have error in third location. So in total 6 bits are there. As per error syndrome, or one can say syndrome matrix, we have error in third bit, right? If we have error at third bit, then you can write error matrix, that will be 0 0 1 0 0. See, in total 6 bits are there, right? So error is there in third bit. See, we have received this y is equals to this that we have received. That was the question that was given, right? So if you receive this, then here we have received a data y. And what is that? This y, that is 1 0 0 1 1. And if you want to correct the error, then what is correction? See, correction is x, that will be e plus y. So if you perform XOR operation over here, then 0 1 1 0 0 0 1 0 1 0 0 0 0 1 1 0 1 1. So that is how one can do correction. So you can observe here in third bit, we have received 0 and we have corrected it. Now it is 1 0 1 0 1 1. So 1 bit error correction that we have performed, right? So here I have explained in total process. You can observe, see, you will be given with generator matrix, right? So based on generator matrix, you can generate code word. So first of all, you need to understand what is generator matrix. That is identity matrix and parity matrix. And based on parity matrix, one can understand what is code word. See, code word is information into generator matrix, and you can write that as per information and PC, where PC is parity code word matrix that can be calculated by information into P. And if you do this calculation, then you can write all the possible code words. Sometimes in question, you may be given with information only. So if you have information I, then by directly multiplying I with G, you can get code word for given information. But here I have generated all the possible code words. And at receiver side, if you have been given with received data, then what you need to do? You need to identify parity check matrix. That parity check matrix, that will be P transpose and identity matrix. And P transpose, that one can calculate based on parity matrix, and identity matrix that you can place. And once you have parity check matrix, you can have syndrome matrix, that will be received data into H transpose. And once you identify this multiplication, then whatever syndrome is there, that you need to map over here with H transpose. And at that location, you can say we have error. Like you see here, we have third row that is getting matched over here. Means at third bit, we have received error. So this is how complete process is there. Now out of this entire process, there can be small questions. So that I'll be placing in future coming videos. I hope you have enjoyed this. Still, if you have any confusion, just place that in comment section. I'll be happy to help you. Thank you so much for watching this video.